I can see everything quite clearly. It has a stark beauty all its own.
Origins of the universe, the Big Bang Theory. In the late 1920s, an astonishing discovery was made. The light from distant galaxies is shifted to lower frequencies, redshift. Much like the sound of a passing train or a car's horn shifts to a lower pitch. The shift in light frequency can be explained similarly. Distant galaxies are moving away from us. In fact, all galaxies, clusters of billions of stars, are moving away from our Milky Way Galaxy and each other, and the farther away they are, the faster they are moving away from us. This is identical to a massive explosion. The bits all move away from the center of the explosion. According to the standard theory, space and time, as well as all matter and energy in the universe, were created in the Big Bang approximately 10 to 15 billion years ago. Following the Big Bang, the conditions in the rapidly expanding and cooling universe were such that only simple matter could form. The universe was mostly made up of hydrogen and a trace of helium. Galaxies formed in areas with higher concentrations of hydrogen and helium as the universe expanded, and stars formed within galaxies in areas with higher concentrations of hydrogen and helium. Stellar evolution. Birth. The mutual gravity of all the atoms in a nebula, gas cloud, causes it to slowly contract. Contraction raises pressure, which causes the cloud to heat up. The majority of the mass falls into the center of the mass, where pressures are greatest. The protostar, the nebula's core, heats up the most and begins to glow red hot. Soon, the pressure and temperature are so high that hydrogen atom nuclei begin to fuse together to form helium. This nuclear reaction generates a tremendous amount of energy. The thermonuclear fires have been lit, and a star has been born. The gravitational contraction is stopped as a result of the energy producing an outward pressure. Death. The star eventually fuses so much hydrogen into helium that the hydrogen concentration in the core decreases, and the thermonuclear reaction slows. The core of the star cools and contracts again. The pressure and temperature of the star's core rise as a result of the secondary contraction. Most stars that are smaller than our Sun will gradually cool and fade. Intermediate mass stars, 0.8 to 8 times the size of our Sun, will begin to fuse helium. This red giant phase of stellar evolution produces periodic table elements via iron. The star's atmosphere is blown away in the form of an expanding ring, planetary nebula, and the remaining star becomes a white dwarf. The pressures and temperatures generated in the secondary contraction phase of high-mass stars 8 to 20 times our Sun are so great that massive nuclei fuse together, forming the largest elements of the periodic table in a stupendous explosion known as a supernova. These elements are spread throughout interstellar space by supernovae, where they can merge with other nebulae to form new stars. The remaining 10% of its mass exists as a neutron star. The mass and thus gravity of very high mass stars, 20 to 100 times the size of our Sun, is so great that when it enters its late contraction phase, the pressure in the interior is so great that matter cannot withstand it. Matter crumbles. A black hole is created. Origin of the Earth. The Solar Nebula Hypothesis. Our solar system formed about 4.6 billion years ago from a cloud of gas and dust that gradually contracted due to the mutual gravity of all its particles. The cloud was primarily composed of hydrogen with minor amounts of helium and the remaining naturally occurring chemical elements. As the nebula contracted, the initial rotation or tumbling motion was accelerated, similar to how a spinning ice skater who pulls in their arms spin faster. The cloud transformed into a disk. The center of the disk had the highest concentration of matter. This eventually evolved into the Sun as we know it. Matter accumulated in smaller clumps throughout the disk. These were transformed into planets. The proto-sun and proto-planets grew from the accretion of matter falling in toward the center of mass. The solar nebula became hotter as the pressure increased, particularly in the inner nebula. The pressures and temperatures in the protocore sun eventually became high enough that hydrogen nuclei fused together to form helium. This nuclear reaction released enormous amounts of energy, and it still does today. The sun was created. The majority of the solar system's gas and fine particles were swept away, leaving only the protoplanets and asteroids. Although the planets had gained the majority of their mass by this point, heavy meteor bombardment continued for another 500 million years or so. The small protoplanets, Mercury, Venus, Earth, and Mars, were too hot to hold the volatile gases that dominated the solar nebula at the high temperatures of the inner solar nebula. Only refractory, high melting point materials such as iron and rocky silicates were stable, so terrestrial planets are primarily composed of metallic cores and silicate mantles with thin or no atmospheres. Temperatures in the outer space nebula were cool enough for the abundant gases to accumulate and be held by protoplanets. As a result, Jupiter, Saturn, Uranus, and Neptune are gas giants composed primarily of hydrogen, helium, and hydrogen compounds such as ammonia and methane. Segregation of the Earth's layers and atmosphere. The materials that accumulated in the early Earth were most likely added piecemeal and in no particular order. However, due to gravitational collapse, impacts, and radioactive heating, the early Earth was extremely hot. As a result, the early Earth was most likely partially or entirely molten. Denser liquids sank to the Earth's core during this molten state, while less dense liquids rose to the surface. Similar to how oil rises to the surface of water, the Earth now has a metallic iron core and a rocky silicate mantle as a result of this process. The Earth's outer crust eventually formed as a result of igneous, volcanic, and intrusive activity. Today's crust is composed of materials with lower density and melting points than that of the mantle. Impacts that penetrated the interior injected volatile materials carried by certain types of meteors and comets into the mantle. The hot early Earth cooled by convection, much like the Earth's interior does today. Convection is now linked to seafloor spreading and hotspots. The pattern of spreading and subduction on the early Earth's seafloor was most likely more vigorous and chaotic than it is today. Because gases do not like to remain in the solid or liquid state, there must have been rapid convective turnover of the mantle, resulting in the rapid release of volatiles stored in the mantle. Gases in the mantle prefer to escape any forming melt, and happily escape into the atmosphere if the melt erupts at the surface. Even today, volcanic activity emits large amounts of carbon dioxide, water vapor, and other gases into the atmosphere, particularly at mid-ocean ridges. Naturally, the majority of the released water vapor condensed to form the oceans. The oceans and the primitive reducing atmosphere were formed as a result of this outgassing. Biological processes have given rise to our oxygen-rich atmosphere over the last 3.5 billion years or so, since the evolution of life on Earth. So that's the end of the video. Make sure to like the video, subscribe to our YouTube channel, and press the notification bell so you never miss out on our next videos. Until the next video, take care.